Hi everybody. I'm looking at how many people are currently on the stream, and it looks like there's only about 6 or so. So I'm gonna let this run for a little bit so that people can come in. We'll get started in about 2 or 3 minutes. So I'll see you for that. All right. I need to get my tablet. I just realized. Welcome back to Chem 140. This is the second to last lecture. There's one more tomorrow, and that's it. We're done. Yeah, believe it or not, we're at the end almost. So, what do we have on the announcements plate? So, quiz number 8 has closed. I just checked and realized that Canvas didn't actually close it because Canvas. So I closed it and I released the answers. Those should be available right now. Make sure that you are checking your quizzes so that you can compare your answers against the correct answers so that you can use that to study. I've been getting a lot of emails from people saying, it'd really help if you release the answers. And I'm like, yeah, I do. They're right there. You can go see them. And I'm sort of wondering how many people actually don't know that you can check your quizzes and see your answers after I have closed the quiz and then release the answers. You can't do it immediately because when the quiz is still going. But I feel like that's something that should be covered in STEM 101, and if it's not, then I need to have a talk with some people. Lab number 4, that's due this week. So it's due Thursday, soft deadline. Make sure you get it in by Friday, sometime that evening. And don't forget to do course evals. Those close on, is that Thursday? Let me look. It's the 4th. The 4th, which is Friday. So make sure you do those. All right, yesterday we did the rest of Chapter 15. We did a little bit of Chapter 16. That's not the right thing. There we go. We started talking a little bit about solutions. What is a solution? A solution is a mixture of two things. And I put this on the screen to show that there are different types of solutions. Remember that the solute is... Oops, that's the wrong tool. Here, hold on. The solute is the thing that you put into the solvent. So solute goes into the container that has solvent in it. For the purposes of this class, the solutions that we're going to care about are going to have the solvent be both in the liquid phase and also be water. And we call those aqueous solutions again. All right, now let's talk about some properties of solutions, like how much can you dissolve in stuff, what are some terms that we use for that, etc., because we're going to be using these. First of all, a lot of people have come together to figure out how much stuff can dissolve in water at any given temperature. So I have this link to a solubility table here, and if I could get the arrow tool out, I'm going to click on this, and I'm going to link it in the chat just in case you want to look at it. But I'm also going to put it on the screen here. Window capture, solubility table. Perfect. Oh, I got to turn it on. And so what this chart tells you is for 100 grams of water, which is 100 milliliters, how much of this substance listed on the left here can be dissolved at this temperature. And so you'll notice that for all of these different substances, they have a range of temperatures where their solubility has been measured. And some things are very soluble. For example, cobalt-2 iodide will dissolve a lot. 203 grams will dissolve in 100 milliliters. However, cobalt nitrate, or nitrite, is not very soluble. 0.4 grams will dissolve. Okay? There's a whole range. In fact, if I go down to this right here, cobalt oxalate, 2.6 times 10 to the minus 9 grams will dissolve. That's like barely a speck. So there's this humongous range of solubility. And we're going to talk a lot about solubility in 163 and a little bit more in 162. Okay, so we can put this away. On the screen, I have shown a graphical representation of solubility by using these lines that tend to increase as temperature increases. And so the general trend is that when you heat stuff up, it becomes more soluble. And the reason for this is because when you heat things up, they tend to move faster. And things that move faster don't want to be in the solid phase. They would rather be in the liquid phase. That's the very short version. If something is moving faster, it has enough kinetic energy to break out of the solid phase. Now, again, we're going to go into that in much, much, much more detail in 161 and 162. Because we're going to talk about how solutions dissolve and how equilibrium accounts for dissolution and recrystallization and things like that. But that's all beyond the scope of this class. So just suffice it to say, as things get warmer, they tend to be more soluble in almost all cases. You see this cerium sulfate thing doesn't get more soluble. This one down here. Oops, I gotta get the pen out. This one down here is an exception, and this has to do with thermodynamics. When you make that solution, the solution gets cold, or something like that. I don't know. I don't know the exact details, but it has to do with thermodynamics. So it's not universally true, but it is very often true. Now, how do we read this chart? Because we need to explore it for a bit of a discussion here. So for our discussion here, I'm going to use this line right here, KNO3, potassium nitrate. If I look at some points on the graph, such as this one right here, that didn't draw because I tapped the pen down too much. What I would see is that at 20 degrees Celsius, I could put 30 grams of potassium nitrate in my solution. And it would all dissolve. It would form a homogeneous solution. There'd be no solid at the bottom. I could put any amount less than that. If I put 10 grams in there, it would dissolve. If I put 20, it would dissolve. If I put 1, it would dissolve. Excuse me. So this region, anything below the curve, will represent a situation where the solution is completely soluble. How much extra credit are the course evaluations worth? I'm going to give you 5 points if we get 80% of the course evaluations in by the deadline. I know people are having trouble with that. At this point, all I can do is direct you to the IT help desk, unfortunately, because I have emailed back and forth with the person who's in charge of this every quarter, and their answer is always, I don't know. Guess send them to IT. And it's super frustrating, and I apologize for that. Our evaluations on our campus are absolute garbo. Not the evaluations themselves, but like how you do it is just garbo. Like, it doesn't work. And as far as I can tell, there's no reason it shouldn't work? Question mark? I don't know. Anyway, if I have the amount shown on this graph or less, the solution will be completely soluble. But if I have more than this amount, then what ends up happening is that some dissolves, but the rest of it does not. So if I were to put, say, 50 grams of potassium nitrate into 20-degree water, which would be right here, this data point right over my arrow, that's way too much. Only 30 of those 50 would dissolve, and the remaining 20 would sit on the bottom. Now, we have terms for each of these locations. So the blue side is going to be our unsaturated side, and the green side is going to be our saturated side. So we're going to say saturated and unsaturated. And you're going to see this on the next slide when I show you pictures of it. Now, if I change the temperature, I change the threshold at which solutions become saturated or unsaturated because more stuff dissolves. So if I increase the temperature to 50 degrees Celsius, then my threshold becomes right here, 87 or something. So I can put it up to 87 grams of solid in here before it dissolves. Any more than that, and it becomes insoluble. These definitions are kind of loose. To be honest, the only definitions that I really personally think are useful are this one, and then everything else is soluble. So I'll highlight the soluble one just to do it, but I honestly don't care about slightly soluble. The only reason that I put that on there is because there is a gray area of solubility. And very few substances fall into the slightly soluble region. They are either extremely insoluble, which means like less than a millionth of a gram dissolves, or they are soluble enough that lots dissolves. So for our purposes, we're only going to label things as soluble or insoluble. On the chart on this previous slide here, everything listed is soluble, because the amount of grams that I can put in there is well above 1. All right. Now, here's the picture, the visual version, I guess we'll say, the pictorial version of what we saw in the previous graph. So for our saturated solution here, so this is saturated. You can see all of the solid at the bottom of the beaker, all the crystals right there. That is excess stuff in this case, it's solid copper sulfate, that did not dissolve. You can stir that all day, and you will not get any more in there because the solution is holding the most that it possibly can at that temperature. You'll also notice that the color is more intense. For a saturated solution, the color visible in the solution, if a color is present at all, will be as deep as it can get. Compared to, say, the unsaturated solution down here, in which the color is less noticeable or visible. And over here is the solid that's being used. So you can compare the solid. Even though the picture is lower resolution, you can see that it's similar. So a saturated solution will hold as much stuff as possible, whereas an unsaturated solution does not hold all of it. You've probably heard the word saturated before. Saturated means can't hold anymore. It has the most. Does the substance stay dissolved if the temperature goes back down? That's a really good question. We're going to explore that in just a second, actually. Because it turns out there is another phase here. We have unsaturated, which is it can't hold anymore. Unsaturated, which is I can put more stuff in. Saturated is I can't hold anymore. But then there's also the phase supersaturated, which is, oops, I have too much. I had to get rid of it. Which you might be thinking, well, how the heck do you get too much? How can you dissolve more than you're allowed to have? Because wouldn't it just immediately become solid? And the answer is, well, no, actually. There's a very specific way to do this. And it has to do with how dissolving and recrystallizing works. When something recrystallizes, it needs to have other crystal present in order to start. If there isn't any crystal present, i.e. it's all dissolved, then you get a very weird edge case, and it's called supersaturation. So let's look at this, and then I'm going to show you a YouTube video of this happening. Okay? So we're going to look at potassium nitrate again. And we're going to suppose that I am at 50, or we'll say 20 degrees. If I put 30 grams in at 20 degrees, my solution is saturated. I can't put any more in there. But if I then heat up the solution to, say, 50 degrees, now it's well below the curve because this is where it would need to be. So all of the stuff in my solution is soluble at 50 degrees. Let's then suppose that we added enough stuff to it so that it was still just saturated at 50 degrees Celsius. So I added like 80-something grams of KNO3. It would all dissolve because that's the solubility of KNO3 at that temperature. But now what we're going to do is, once we've ensured that it is dissolved completely, we're going to let it cool back to room temperature. And the question that we're going to ask is, what happens to the solution? Now, according to the graph, we're in the saturated region. What should immediately happen is that it undissolves our solid until there are only 30 grams remaining. But it turns out it's a little more complicated than that for the reasons I listed before. In order for something to crystallize, you need a site for it to crystallize onto. Ions in solution, when things are dissolved, and I showed you this in lab number 3 on that picture, they just sort of bounce around, constrained by water. They need to find another such place where water is not blocking them so they can recrystallize. So what ends up happening here is that while it's in this unstable state, where it's trying to crystallize but it can't because there's nowhere for it to do so, our solution is called this, supersaturated. Now, I'm going to make an analogy here, and very few people have probably done this. But if you try to boil water in a pot that's perfectly smooth, like really new or something, you might notice that you get the water temperature really, really high, and then nothing seems to be happening. It doesn't boil until maybe you bump it or you drop something in it, and then suddenly everything just boils all at once, and it scares the shit out of you. Has anyone ever had this happen to them? No. Okay. Well, it's not as dramatic. Sometimes I get students that are like, holy crap, I've done that once when making tea. And I'm like, yeah. So water boiling does the same thing. When something boils, it needs a place to start boiling for all the gas to accumulate. And if your pot is perfectly smooth when you're heating your water, it doesn't boil and the temperature gets hotter and hotter and hotter until you add a place for it to form, which would be some sort of nook or crevice or irregularity. Instant Coke slushy thing. You know, I am not exactly sure what meme that might be referring to, but it makes me think of this. So I would say yes question mark. Oh, freezing. Yeah, this is basically freezing. What we're doing here. Yeah, if you chill it down and then like you open it or bump it or drop it and then it goes foomp and it freezes, that's exactly what's happening. Yeah. I have seen that. Yeah. Like you drop it on the floor and it becomes ice or something. Like the bottle, not the soda. All right. So what you have is a solution that is considered to be unstable when these things happen. And then when you give them energy or a means to do what they need to, either boil or solidify or recrystallize in this case, the recrystallization occurs. Okay. So we're going to watch this video here. I got to get the cursor. This is sodium acetate. Sodium acetate is... It's also known as hot ice. But what it is it is something that is extremely soluble at high temperature and extremely insoluble at low temperature. So it's very easy to make these supersaturated solutions. So what we're going to do, and you can kind of see it in this guy's reflection, he is going to add a small amount of solid sodium acetate to a crystal here. It's right here on the top of on the tip of his spatula. And so I'm going to just slowly advance the frames as he puts it in the solution. Okay, so there it is in the solution. You can see the stuff that's on the tip of it. Actually, what you're seeing is it's already crystallizing. And when you let it sit there, this is what happens. So if this is like the soda thing that you saw, except a lot slower. So that's sodium acetate crystallizing in a flask. Now, this is what this would actually look like if we just added the sodium acetate into the water, except it wouldn't look as pointy and pretty. But you would be able to dissolve very little of it in water at this temperature because there is just this much in here. In fact, there's so little sodium acetate soluble in there that you can get these really weird structures when you pour. I gotta find the video here because maybe it's not in this reference here. Fun with sodium acetate. There it is. You can tell it's a very serious video based on the font. So I presume that this was some students' science fair experiment demo that they did for like a school, and then they put it on YouTube, and it just happens to be a really good video. Yeah, you can totally stick your hand in it, but the problem that you'll face is that it's really hot. Like 52 Celsius is like, you don't want to be in that temperature of water. That's like, what temperature is 52 Celsius anyway? I hit the wrong button. I don't want to cover up the video. Let me hit play on this, and I will look this up in another window here. That didn't work because I covered it. 52 Celsius to Fahrenheit. 125 degrees Fahrenheit, which I think is quite hot. Yeah, that would be very, very painful. Now, here's the inside of it. I'm actually going to hit pause here. You can kind of see the water in here. A little bit, like as you turn this solution, or as you can turn the solid, you can see the water reflecting off of it. There's not much water there. There is so much solid dissolved in this. Now, if you pour it, it looks really damn cool, because it crystallizes into something that's far less dense than it was in the liquid phase. And so it looks like what you're pouring is more than what you were pouring from. Now, if you're not careful with this happens. And then I don't know what you're supposed to do. But yeah, if you touch this, there's no chemical harm, but it is extremely exothermic, so you will get probably first-degree burns. Maybe second-degree burns. Can you make this easily? Yeah, you just buy sodium acetate and water. The end. There you go. So that's sodium acetate. And there are all sorts of other things that follow these sorts of recrystallization property rules that we exploit. So yeah, you're right. Handwarmers are an example of this. Handwarmers, I don't think, are specifically sodium acetate, because that might just be too exothermic. But it is a very similar premise where, like, you allow two chemicals to mix, and then it gets hot because the solution inside crystallizes. Also, cold packs do that. When you allow solutions to dissolve in each other, the opposite happens. Heat is absorbed and it becomes cold. I know ammonium acetate or ammonium nitrate, one of those, is used for cold packs. So there's all sorts of crazy stuff that we can do with solutions. All right. So to summarize, we can make solutions out of anything. We're going to work with aqueous solutions. Solutions have either the property of being unsaturated, saturated, or supersaturated, depending on their state. It takes effort to get a supersaturated solution. And you can only have a supersaturated solution if all of the solid has dissolved and you then cool it. If it hasn't all dissolved and you have any solid left over, then when you cool it, that solid will just start to recrystallize immediately, because there is a site for crystallization to occur, as you saw in the video. All right. I don't care about those questions, so we're just going to move on to the solubility rules. They're just basically list the solute and solvent. You can do that on your own. That's easy enough. Now, I'm calling these the solubility rules in air quotes. But in reality, there's not really rules to these. There's just certain patterns that we've sort of noticed. And so I opened this discussion by saying solubility is kind of weird. There are a lot of exceptions. Here's a table. I don't make you memorize the table whether you're in class or online, because it's a weird table. Like, committing this to memory, especially in the last week of class, would be extremely obnoxious. Don't do it. Just have this chart handy. because it is extremely useful for predicting phases of substances. Remember how before when we were talking about balancing chemical equations, I said, don't worry about phases. Now, if I were in a classroom environment, I would say, yeah, worry about phases, except I don't know how to evaluate or assess that on Canvas when it won't let you do subscripts and stuff like that. So the way that this works in regards to phases, if a substance is soluble, you would write AQ. If the substance was insoluble, you would write S because it stays a solid. Now, you might ask, what if it's soluble partially, or what if you don't put much in there, or whatever? Then you would put whatever you're supposed to write for putting a small amount of it in there. If you put a small amount, like say a gram, and it dissolved, write AQ. If it didn't dissolve, write S. Keeping in mind that everything dissolves to some extent, even if it's like at the microgram or nanogram scale. We're going to just say, okay, if about a gram dissolves, it's soluble, and if about a gram doesn't, it's solid. All right. How do I read the solubility chart? There's two sections listed. There's soluble and insoluble. What you're going to do is you're going to look up a certain ion in the chart, and if you see it, you then check for an exception. If the exception is present, then it's not the thing you looked up. So, for example, let's suppose I had sodium fluoride. So I would look up in the chart. Okay, where are any of these ions? I would look for sodium, which is this, and I'd look for fluoride, which is that. I don't see fluoride anywhere in here, but I do see sodium, which is a group 1A cation. Group 1A cations are soluble. There are no exceptions. So everything paired with sodium would be soluble. Let's do another one. I'm trying to think of ones that aren't going to show up on the next slide here. Let's do calcium. Let's not do calcium. Sorry. Let's do lead iodide. And so I would break this into ions. I hope we all know how to do that still, because that was chapter 8, or unit 8. And now I gotta look for stuff in the chart. So here's iodide. Iodide is soluble unless paired with one of these things, of which we do have one. So PbI2 would be insoluble instead. Okay, that's the general gist for this. So if you have the slides open on your computer or like in front of you or whatever, that's going to help you in a second here when we do these types of problems. Now, for substances that are not ionic, we don't have a solubility chart. What we have is instead is this phrase, like dissolves like. And what that means is that if something is charged, it will dissolve in water, because water, believe it or not, actually shows parts of charge. And this is a property called polarity. We're not going to talk about polarity in this class. We're going to talk about that in 161. But you can think of water as like sort of the midpoint between being ionic and being molecular. And if you're saying to yourself, well, wait a second, I thought water was covalent because it has only nonmetals, so it doesn't make any ionic bonds. And my response to that is, that's correct for this class, but when we get to 161, we'll learn that it's a little more complicated. And that ionic versus covalent isn't binary, it's actually a gradient. And that there's a region in between where a lot of things actually fall. And they have interesting properties. In fact, those properties are responsible for life, so We'll study those in 161, and then again in Bio 211 when we get to cell bio. So, for example, if I tell you which things are polar and which things are nonpolar, you can think of them as, oh, polar things are charged and nonpolar things aren't. So, for the purposes of this class, think of polar as, oh, it has charges, and nonpolar as no charge. So what that means is that ionic compounds will dissolve in polar substances. So if I had ethanol, I could dissolve salt in it. But if I had hexane, I could not, because hexane is nonpolar and would not dissolve something with charges. And then you just use like dissolves like. So if I have two things that are the same polarity, like oil and grease, they're both nonpolar, they would mix. But if I mix oil and water, one is polar and one's nonpolar, and they won't mix because they're not alike. And again, we'll talk about that more in 161, but this is the general overview of solubility that will help us for this class. So let's do some examples using these solubility rules. So the first example we're going to do is acetone is polar, water is polar. Will they mix together? Yes or no? And if you paint your nails, you already know the answer to this because this is what we sell you to remove nail polish. Yes. Yes is correct. Acetone and water will both dissolve in each other. This is nail polish remover. Nail polish remover is essentially like 80% acetone and 20% water, though you can get pure acetone. How about these two? I have cooking oil. Let's say canola oil, because that's just what I was cooking with when I made potatoes last night. And I pour it into carbon tetrachloride. Will cooking oil dissolve into this substance you've never heard of, based on what I've described here? Oops, I revealed the answer there. They're both nonpolar, so they will dissolve into each other. Because all they have to do is match. Whether they're polar or nonpolar, we don't care about. As long as they match, though. All right. Now let's go on to these compounds where we have to use that chart. So barium chloride is added to water. Will it be soluble? Here's what I'm going to try and do. And I don't know how effective this will be. Slides, Unit 16. I want to capture the PDF. And we'll scroll down to this thing and make it really big. And then I'll do that. All right, so I'm gonna be doing this a bunch, just to like hide stuff so that you can see it. All right, will barium chloride be soluble in water? Yeah, there's some. I keep saying Twitch delay. There's some lag today. Yes. So how did you get yes on that? I can't actually point on that. I guess I could do this though. Okay. Can I draw on this? Will it let me draw on here? No, it won't. Okay. Cannot draw on the PDF. Okay. So barium chloride has barium 2+ and chloride minus. Chloride is soluble. Ooh, maybe I can't draw on this. Chloride is soluble. Barium is not an exception, so we would say that barium chloride is soluble. How about calcium carbonate? Will calcium carbonate be soluble in water? Can I undo these? Yeah, I can. Okay. So calcium carbonate, let's look at the chart. So I gotta find calcium and I gotta find carbonate here. So here's carbonate. Calcium carbonate is insoluble. Is calcium an exception? It is not. So we would say that calcium carbonate does not dissolve. There we go. What is calcium carbonate? It is chalk or Tums. Yes, believe it or not, when you were eating Tums, you were eating chalk. But dum chalk didn't like. It's not as good of an advertising jingle, I guess. I don't know. We got ammonium phosphate. Will ammonium phosphate be soluble in water? So let's find it. Where did the PDF go? There we go. So undo. We got ammonium and phosphate. So here's ammonium, and here's phosphate. What do you do when you got two of them? Well, if you have both, follow either. They will lead you to the correct choice. So I'm going to follow phosphate. So phosphates are insoluble unless paired with ammonium. Now, if you'd gone the other way, you would have found that ammonium is soluble with no exceptions. So in either case, the outcome that you get for this is that, yes, this is soluble. NH4 is ammonium. Yeah, it's a polyatomic ion that we used in Unit 9 when we did nomenclature. So it should sound familiar. All right, so here's what I want you to do. Oops, I didn't mean to do that. I want you to determine which pairs are soluble or insoluble in each other by using the solubility chart or using like versus like, or like dissolves like. Okay, so enter in the chat whether the pairs are soluble or insoluble in each other. Let me number them for you so that it's... And you'll have to go back to that chart. If you don't have the chart handy, what I'll do is I'm going to leave this on the screen for about a minute so you can write it all down, and then I'm just going to go boop and put the chart on the screen so you can see. Okay? So go ahead and write all those down, and in just a moment, I will come back and put the chart on the screen for you to look at, and then we'll go over the answers. So see you in a bit. All right, I'm going to put the chart up on the screen now. And if you still need to write stuff down, you can always rewind the video. All right, one more minute to finalize your answers. Yes, no, maybe, I don't know. Can you repeat the question? You're not the boss of me now. That's going to give me a copyright strike, isn't it? Oh, well. All right, so I got to get this off the screen so that I can write on it. So for benzene and hexane, both of them are nonpolar. So they should dissolve in each other. I'm going to write yes for they dissolve in each other. Oxygen is nonpolar and water is polar, so these do not dissolve in each other. Now, I'm going to immediately hit the brakes here and go, wait a second. If oxygen is insoluble in water, how do fish survive if fish need oxygen? Anybody have any idea? We just showed that it's insoluble. And this is the correct answer. So what's the deal here? Magic. Yes, fish are magic. While correct, that's not the answer that we're looking for. So even though oxygen is insoluble in water, remember that insoluble does not mean zero. So a small amount of oxygen does get in the water. However, when I say insoluble and small amount, I do mean a small amount. There's very little oxygen dissolved in water. And fish survive on that. That's why fish are so dumb. They don't have enough oxygen. Now, interestingly, oxygen is more soluble in cold water than it is in hot water. Which makes sense because if you heat stuff up, it wants to become less solid-like, right? Oxygen would be a gas at any temperature, and thus it would move even faster at a higher temperature, which means it would only dissolve if it was going slow. So more oxygen goes into the water if it's cold, which is why fish prefer colder water. If you have water that gets too hot, for example, global warming, the oxygen dissolves out of the water, and then all the fish will die. And then we don't get to eat them. Or, I should say, we will have a feast on fish for a very short time, and then all the fish will be gone. And that would be bad and sad. So we should probably try to keep the environment a little bit better than it is. If only so we can keep eating fish. Sodium nitrate, according to the chart right there, you can put anything with nitrate or anything with a group 1A cation like sodium, and it will be soluble. So this is yes. That's not the pen. There we go. Fish are friends, not food. Who says they can't be both? Potassium is a group 1A, so it must be soluble, just like how sodium was. I think we already did lead chloride here. So chlorides are soluble unless they're paired with lead, according to the chart. Let's go to the chart to confirm that. So you can see there that chloride on the third row of soluble is soluble, but unless it's paired with lead 2+, which it is in this case. Oops, that's goodbye. I removed everybody. Click the wrong thing. This one I don't remember. Hydroxides are generally insoluble, but when they're paired with barium, well, let's see. So hydroxide at the very bottom, insoluble, but paired with any of these things, they are soluble. And barium is one of those. So we would say... Oh, sorry, we would say no here. This one's yes. And then this last one is sort of a trick. Here I got NaCl, but I'm not putting it in water anymore. I'm putting it in benzene. And you'll notice that benzene up here is nonpolar. And remember how I said earlier, things that are nonpolar should be thought of as doesn't have a charge. Well, NaCl is ionic. And benzene is nonpolar, so these don't mix. They do not dissolve. I'm not going to test you on number 7 in class, or on the quiz, or the exam, obviously, because that's sort of beyond the scope of this class, since we're only dealing with water. But just as an FYI, if you mix salt in other liquids that are nonpolar, nothing will happen. So if you put salt into a gas tank, it won't dissolve, because the gasoline and the salt are insoluble with each other. Not that you should put salt in a gas tank, because it won't combust either, and then it just kind of corrode your gas tank. The real problem is sugar, because sugar contains nonpolar parts to it, and sugar will dissolve very well in gasoline, which is why putting sugar in a gas tank is something you should absolutely never do. Never do that as a prank to anyone. Never. No, sir. Don't do it. You did not hear this from me at all. You know, maybe we should just take a break. That's the wrong button. All right. When we come back, we're going to start talking about concentration by using numbers, which means we're going to do math. So we'll see you in a bit for that. I didn't find the music in time. Hold on. Music, music. What music do we want? Death Mountain. There we go. Wait, what the heck? Look at that. Hold on. I actually landed on 10 minutes. Yay! We'll have our little victory song there. All right, back to work. Oh, first, though, I have to tell Steve that I have to lecture, so back to lecture. Talk in a bit. Otherwise, it's just going to keep going chime, chime, chime in my ears. Let me turn that music off so that you can't actually hear that if he messages me. All right. So, what we're going to do, we are going to now represent the amount of stuff in a solution, whether it's saturated or unsaturated, and how much, with a number. And we're going to use some terms to describe the size of these numbers first, and then we're going to assign actual numbers to them. So we're going to call something that has a large amount of solute with a high concentration concentrated. So concentrated solutions will have large numbers assigned to them for how much stuff is in them. Whereas a dilute solution, which is the opposite, doesn't have as much. So something is dilute if it is less concentrated than something that is concentrated. So we're going to... Uh-oh. Everything is showing... hit rewind, and it should all be in the screen. So how do you dilute something? Well, you just add water to it. And the way that this works is that if you have something that's concentrated, you have a lot of solute per unit volume. And so you could see my solute here, right here in this container. There's not much space between it. Oh, so in the concentrated solution, their molecules are closely packed together. There's more of them per unit volume. If I were to add water, the molecules then spread out, and there's space between them that makes it more dilute. Okay. In these pictures, the solute is what is shown as the green blobs. The water is the interstitial space between all of the molecules. So you could make a solution dilute by putting water into it. How would I make something more concentrated? How would I do the opposite of putting water into it? Any idea? I'll give you a hint. You do this in cooking. So you could add more solute, but maybe you don't know where it is or it's expensive or something like that. If adding more water dilutes the solution, yeah, you would remove water to concentrate the solution. So you'd heat it up. You could boil the water away. Now, that assumes that the stuff is it's not that soluble, that it's stable and it won't decompose at a high heat. But most stuff is pretty safe. So if you want to concentrate stuff, you reduce it. So in cooking, there's a technique called reduction, which is whenever you're making like a sauce on your pan, you heat it so that the water comes out, but the rest of the stuff that's all the flavors and the good stuff stays there, and its volume gets slower and it reduces. So this is common when you're cooking with things like wine or cream. Those are the ones that I use predominantly. Chicken stock. Chicken stock, that's another good one you want to reduce. So last night I made chicken pasta, where you put a bunch of chicken stock and tomatoes into the pan, and then you just let almost all of the water boil out, and you get this extremely chickeny, tomatoey thing. And then you pour that all over pasta, and it's so good. All right. So those are the two things that we can do to solutions. We can add water to dilute, or we can remove water to concentrate. How do we express concentration in a number? We use molarity, and so the formula for molarity didn't actually show up. Hold on. Let me fix that, because this issue keeps cropping up. Alright, so I want this. And custom animation. Yeah, I don't know why it showed up last. In fact, we don't even need that to animate. There we go. That should not be on the screen now. There we go. Here's how we express molarity. Molarity is moles of solute divided by liters of solution. In other words, how much solute did you put in there? Figure out how many moles you have. And then how much solution in total do you have? Calculate its volume. Now, it's important to note that the bottom part of this expression is the solution and not the solvent. So if I told you that I put 5 grams of salt and 100 milliliters of water together and asked you to find the molarity, you can't actually do that because you don't know the volume. You'd have to add the volume of the 5 grams of salt, which could be whatever it is, to the 100 milliliters of water. And then there's another problem that we're going to run into when I talk about how to do volume calculations later on, and that is that volumes don't sum together. All right, let's worry about that later. We'll talk about that when we get to that part of the lecture. We're going to calculate the molarity of this solution. We're going to take a 2 mole sample of calcium chloride and put enough water in it to form 1.75 liters of solution. Note how I said I'm putting enough water to form this much solution, and I did not say I added 1.75 liters of water, because those are different things. It seems like they aren't, but they are very different. Okay? So, let's go over here. That didn't work. There we go. All right, there we go. So remember that the definition of molarity is equal to moles of solute over liters of solution. And so I know that I have 2 moles of calcium chloride. And the volume of my solution in liters is 1.75 liters. So all I have to do is divide these two numbers. That's easy enough, right? 1.142. Now, because the units do not cancel in this case, we write both of them. However, there is another way to write this. Instead of writing this part right here, moles per liter, over and over and over, the unit that we use for this is capital M. So you can either write moles per liter, or you can write giant uppercase M. Either one is acceptable. That's the most basic molarity calculation that you could do. We're not going to be giving you amounts in moles very often, though. In fact, much more common, you'll be getting things that are in grams. So you'll be asked, like, if I put 20 grams of the substance into this many milliliters of solution, well, you'd have to convert milliliters to liters, because molarity needs liters. And then you need to turn grams into moles, because molarity also needs moles. All right. Let me get this off my screen there. So as we go through these calculations, we're going to be doing more calculations with molarity. So you're going to see this come up again. But the gist of molarity itself is pretty straightforward. Always write down that formula until you have the idea figured out. All right, so how do we prepare solutions in the laboratory? Let's suppose that I wanted to make a 1 molar solution of sodium chloride with a 1 liter flask. So the first thing that I'd have to do is figure out how much sodium chloride I wanted to work with. Well, let's actually calculate that out as another example. So again, we'll write down the formula. So molarity equals moles of solute over liters of solution. Now, let's suppose that I wanted to figure out how many grams of sodium chloride I needed. Well, I know the molarity, and I know the volume, according to this problem. So I could do this in the following way. If I multiply both sides by the volume of the solution, I would get, here's my molarity of my solution. I want 1 mole of sodium chloride per liter times the volume of my solution, 1 liter. The liters cancel out. And I get 1 mole of sodium chloride in my solution. That makes sense since the whole thing is just ones, right? But now I got to turn that into grams. So then I could say, okay, well, in 1 mole of NaCl, there are some number of grams of NaCl. Where do I get that number? You get it from Lentech. Maybe that's the wrong number, actually. Did I do iron again? I don't know. 35.443 plus 20. Oh, no, that's right. Okay, cool. Oops, hold on. I have too many sig figs. There we go. So there you go. So in a 1 molar solution of sodium chloride with volume 1 liter, I would have 58 grams of sodium chloride. So if I wanted to make this solution, I would need 2 things. I would need this amount of sodium chloride, and I'd need a 1 liter flask, and I just put one in the other, right? Now, it's a little more involved than just adding one to the other, because you got to put water in, and you got to put things in the right order so you don't overfill the flask, etc. But for the most part, that's what you do. Weigh out your 1 mole of sodium chloride, which is 58.44 grams, which we calculated. To 1 sig fig, it's just 58 grams. Once that's in there, you're going to add enough water so that the total volume of the solution is 1 liter. And the way that you do that, at least to be most efficient at this, is you're going to put the water in this container first, just to make sure you've washed out all the salt. You don't want any of that to be left over. Pour that into here. Then you're going to wash off the beaker or the funnel and the rest of the thing. And then you're going to slowly add water until you hit this part right here. Once you've done that, the total volume at this point will be 1.0 liters. But the solution will not be homogeneous, and so you have to do this right here. You got to mix the solution. Now, ironically, that's the most important part. If you're off by a slight amount of water, like you overshoot or undershoot by like a drop or two, that's probably okay. But if you don't mix the solution and you immediately go to use it, the top part's going to be all water and the bottom part's going to be all salt, and you're going to get very, very different results. So preparing solutions in the laboratory for use in an experiment does require you to make sure that your solution is homogeneous. And mixing accomplishes that. You know, for all of the solutions that we're going to be making this quarter, right? If this were an actual, like, lab class where we were participating in the lab, you would actually be making these solutions today. And then you titrate them. All right, so let's do an example here. Let's suppose that you want to make a 3.5 molar solution of KBr, and you still want 1 liter of solution. What I want you to do is tell me how much KBr you need to put in the flask. So use the expression for molarity that I just showed you, and figure out how much KBr you need in grams. And then what I want you to do is describe how you'd make a solution in a few words or pictures for each of the steps. So first, weigh out the stuff. Second, what do you do with it? And then third, mix. The third step should just be mix everything. Okay? So go ahead and try that, and we'll go over the answer together in just a moment. All right, let's go over the answer. I need those numbers. Oops. All right. So I want to make a 3.50 molar solution of KBr in H2O, and I want to have 1 liter of solution. So let's start by writing down the formula for molarity. Molarity is equal to moles of solute over liters of solution, which I can then rearrange to take molarity times the volume of the solution will equal the moles of solute. So my molarity is 3.50 moles of K, what is this, KBr, per liter, times my volume, 1 liter. So that will give me that many moles of KBr, which I can then say, okay, KBr, grams KBr. In a mole of this, there are some ginormous number of grams. I don't actually know. Where is Lentech? There we go. KBr. 119.00. I get 417 grams KBr. All right, so now we can describe how to make the solution in words or pictures. So here we go. Step 1, add 417 grams KBr to a, oops, I looked at the wrong number. A 1 liter flask. So we're just going to dump that in there. There it is. That was the sound it makes when you dump it in. Step 2 is we're going to add H2O. We're not going to add a specific amount of H2O, though. We're going to add H2O to the fill line, which is 1 liter. We're going to mix it really well. And then the solution is done, but there is a 4th secret step here that you don't really need to include. And that is enjoy. I put enjoy there because students like to remember weird things, and that helps them. Like, oh, right before I enjoy, I mix really well. Before I do that, I do something, or whatever works for you as a mnemonic for you. So. All right, that's how we make a solution. Let me know if you have any questions. All right, for the next part, we're going to do a few more calculations using molarity. Now, molarity is super useful because it is a ratio of moles and volume, which means that it is a conversion factor, just like density was. And so what we're going to do is we're going to use molarity to figure out how many moles are in a sample given its volume. Because if I multiply volume by molarity, you get moles. And you could see that on the preview right here, where we did this first thing. Here I had molarity times volume equals moles. So keep that relationship in your back pocket because it is going to be very handy for the problems that we're going to do. Okay. Speaking of problems, let me just advance this a little bit. All right. So let's do a volume that is not 1 liter. In fact, we have a volume that isn't even in liters this time. We have 500 milliliters. So let me clear the screen. Yeah, my favorite, wet potassium bromide. All right, so what do we got here? So we know that molarity times volume equals moles. Now I can just start abbreviating these things with what they are, right? So let's write this all out using what's on the screen here. So I have 0.350 moles of, what is this? Magnesium hydroxide per liter. That's my molarity. And I have 500 milliliters of solution. You're going to notice really quickly that those don't cancel out. So if you multiply them together, you're not going to get the right answer, right? What should we do? Well, we should convert this volume right here into liters by multiplying it by this, right? Yeah, milliliter is 10 to the minus 3 liters. So these will cancel out. And now these will cancel out. They don't have to be next to each other to cancel. They just have to be on opposite sides of the division line. Where's the division line for 500? Well, it's just a number by itself. It's like dividing by 1. And so if I multiply all these numbers together, I will get the number of moles. And there you go. And if you needed to figure out how many grams were in the sample, you could just turn that into grams by converting moles to grams. That's straightforward enough. All right. So now that you know how to get moles out of something, here's some different types of questions using different applications of molarity and the molarity formula. So what I want you to try and do is answer these 2 questions here. So, well, there's 4 actually. So I have a beaker with 35 milliliters of this molarity acid. So how many moles of HCl are in the beaker? And how many grams of HCl are in the beaker? And then the second problem ties together all the stuff that we did in like unit 11 and 12. I have a volumetric flask with 250 milliliters of solution. The solution is 3 molar potassium dichromate. What mass of potassium dichromate was used to make the sample? What is the mass of only the chromium atoms in the solution? You can actually solve these problems now, believe it or not. But it might take a little bit of thought. So give it a shot. We'll go over the answers together in just a minute. Sorry, I wasn't actually looking at the screen. I'm just reading Twitter. Looks like some people have some answers. So I'll give one more minute and we'll go over the solution. I actually need to fill my water, so let me go do that, and then I hit mute before I finish talking. We'll go over the answers. So see you in a bit. All right, so let's do this. That's the wrong problem, so let's get this one on the screen first. All right, so I got 35 milliliters of 2.50 molar HCl. So remember that molarity times volume equals moles. And so that would be 2.50 moles of HCl per liter times the volume. But we want the volume in liters anyway, so I'm just going to immediately convert that to liters. That's 35 times 10 to the minus 3. So now those cancel out. We get... That's not what we get. 0.0875 moles. So there's answer 1 right there. And then I want to find out how many grams of HCl are in the beaker. So I would then go 1 mole HCl. How many grams of HCl? Which I believe is this. And I get 3.19 grams HCl. Sweet, that's the first problem. No problem there. All right, let's look at the second one. What's the mass of potassium chromate used to make the sample? So we're going to do the exact same thing. We're going to go MV equals moles. So we'll start with... There's our molarity. We'll multiply it by the volume. It's 250 milliliters, so that's 0.250 liters. Do I have the wrong number of sig figs on the first one? Should have 3. This is 3. Okay, cool. Yeah, these are all 3. All right, so this will be the number of moles that I have. I could just get an answer and then turn it into grams, but we could also just do the conversion straight over here. So I want to cancel that unit, so I'll just put moles of K2CR2O7 here and grams of K2CR2O7 here. I don't even want to begin to try and guess what the number of grams per mole that is. K2CR2O7. I got 294.18. And so I got 220.6, which becomes 221 grams of potassium dichromate. Okay. Then for the last question here, it's asking, what is the mass of only the chromium atoms in the sample? Now, this would be possible to go from here. I could go grams to moles, and then moles of chromium, and then grams of chromium, right? We could do that. But it turns out that this result right here, moles of K2CR2O7, is actually, we'll put this in green here. That's just this right here, isn't it? Because that's what we started the problem doing, was we calculated the number of moles of K2CR2O7. So instead of doing the calculation again, I'm just going to take this number, whatever it is, and I'm going to multiply it by moles of K2CR2O7, so that this unit cancels out with this again. Moles of chromium. And within one of these big molecules, there are 2 moles of chromium. Hopefully we remember that from Unit 11 or 12. There's 2 chromiums in the big molecule. And now I can just say, okay, in a mole of chromium, there are how many grams of chromium according to the periodic table? 51.996. Those units cancel. And so now when I do the calculation here in green, which is this plus this, all of those multiplied together, I will get the answer to this problem. 3 times 0.250 times 2 times 51.996 divided by, it looks like all ones, so 78.0. That's the wrong color. 78.0 grams of chromium. Which is a really cool little application that you can do. Just to keep you on your toes to answer questions like that, should they appear on some assessment later on in 162 or whatever. All right, any questions on how we solved these types of problems? So this is one application you can do with molarity. In the next section, which is dilutions, we're going to cover another application. And then in the last section, we're going to go over more problems with molarity and stoichiometry. So I was just looking through here to see what was coming up here. Well, I mess up the exam if I do that. That's close enough, I think. So if it's 3 sig figs and the answer was 221 and you put in 220, as long as you're within 3 on the last digit, I accept it. So you could have put 224 or 218 and those would all work. Any number between those ranges would work. All right, let's do some last practice with molarity, and then we'll save dilution and titrations for Thursday. That's when we'll talk about the lab, is on Thursday. So we already know that you can use molarity times volume equals moles. Here it is just officially now. So let's just do some more of these types of problems. This calculation, in fact, these calculations are pretty straightforward. You could do these examples on your own, so I'm not going to work through them because we literally just did these problems. I'm going to just put these on the screen here and ask you to solve them, and we'll go over these answers together. Just because there's only 9 minutes left, and I want you to be able to do some more practice before we go. So, a solution of calcium bromide is made to be 1.5 moles per liter. How many grams are in 100 mils of the solution? What volume of calcium bromide solution is needed to obtain 5.75 grams? And then finally, a jar of KBr has 39 or 35.9 grams of KBr. How many liters of 0.8 molar solution can be made? These are all manipulations of the molarity formula, so try using the MV equals moles and solve for the appropriate thing that you need. And then answer the question as written. So I'll give you 4 or 5 minutes to do that, and then we'll go over the answers, and then we'll call it a day. How are we doing? There's only about 3 minutes left, so I'm going to go over the solutions so that they are in the video. So you can keep working. You just mute me if you want to keep working. And then go back and watch later. Or hit pause, I guess. Pause would do the same thing. All right, so I have a solution of 1.50 molar calcium bromide, and I have 100 milliliters of it, so we'll do MV equals moles. You can't see that because it's off the screen. So my molarity. You'll notice that I'm writing out the units every time, and the reason for that is just to make sure all my bookkeeping is in order, so that when I multiply all this stuff together, if the units cancel out, it's going to work. Here's 100 milliliters. I have turned that into liters just so this happens. And then I want to turn this into grams, so I'm going to cancel this unit out. And turn it into that unit. So moles cancel, leaving me with grams. How many grams are there per mole? I'm not typing that into anything, apparently. CABR. 19989 is what I got. 0.89, sorry. And so this would tell me the number of grams that I need to make this much solution. 30.0 grams calcium bromide. Okay. That's the first one. Let's do the second one. What volume of calcium bromide is needed to obtain this many grams? So I'm going to write down the equation again. But now I'm going to solve for volume here. So I'm going to say volume is moles divided by molarity. Well, first I need the number of moles, which would be this calculation here. 5.75 grams calcium bromide times we'll just do that. Grams per mole. So this unit cancels out with this unit. 1 mole is still 199.89 grams, because that's from up here. It's the same number. So everything in the parentheses, we'll put green parentheses around them here. That's my moles. When I do the calculation, I will get moles out. And if it helps you organize, you can do the number, hit enter, and write it out with moles. I'm going to divide all of that by the molarity, which is 1.50 moles of CaBr2 per liter. Now remember, when you divide fractions, it's like multiplying by the reciprocal, so I could put this up here at the top instead and do it this way. And now you'll notice that, oh, this very obviously cancels out with this, leaving the only unit that I have left here. So when I punch all that out, I will get a value in liters. 5.75 divided by parentheses 199.89 times 1.5. And I get 0.0192 liters, or 19.2 milliliters. And so this is the part of the class where it's like, okay, if you write all your units at every time and just make sure everything cancels, you're going to do it right. All right, last two problems, or the last one problem here. A jar of KBr has 35.9 grams left. How many... Oops, I got to go back up here. How many liters of 0.8 molar solutions can be made? So again, MV equals moles. Again, we're solving for V. So how many moles can I make? Well, that would be 35.9 grams KBr times grams KBr, mole KBr. So these cancel, leaving me with moles. And 1 mole KBr, I forget the molar mass. I think it's 119. That didn't work. KBr. 119. So that in parentheses would be moles, because that's the only unit that's left. We then, again, divide by the molarity, which would be like this. Do the same thing. You could just then multiply by the reciprocal. It would be liters over 0.8, but we saw that the units cancel out when I do that. So I'm just going to punch the numbers in as shown. 35.9 divided by 119. That result divided by 0.8. So with the remaining quantity of KBr in the jar, I could make, at most, 377 milliliters of 0.8 molar solution if I used all of it. I could use less and still get a 0.8 molar solution. But yeah, these problems are just exercises in, hey, can you manipulate the units? Because the concept isn't hard. Moles divided by liters is not a difficult thing to do. Everybody can figure out the molarity of a solution, which is why we did one whole problem on it. But it's doing all of these different manipulations with molarity and playing around with the units. This is why we did all of that shit in Chapter 3, where it was like, how many miles can Grim ride his motorcycle? Like, nobody gives a crap about that except me, right? I'm the person who wrote the orc into existence. Nobody cares about his motorcycle or how the circumference of his tire or how many centimeters it is to Everett. Like, nobody cares. But by doing that practice of manipulating those units in these weird situations, you are now in a different weird situation because you've never seen these units before. Until today, anyway. But you can still manage them. So that's sort of why we did all of that prep at the start, where it probably didn't feel like it was a chemistry class. Now we're using that knowledge here in actual chemistry. I want to thank everybody for coming out to the lecture. I apologize for going over by like 6 minutes. Jeez, I'm just getting longer and more long-winded, I guess. Come back tomorrow for the final lecture of the quarter. After that, it's all just review sessions and exams, really. So, I will see you for that. Let me know if you have any questions. Send me an email. Remember that you can take quiz number 9 tonight if you want to. It does have these types of problems. You might want to wait until Thursday because it is set to only 2 attempts. But do try to take the quiz on Thursday or Friday, and feel free to ask me questions about any questions on the quiz number 9. Because it's open, I'm happy to answer any questions at any time up to the exam. During the exam, I can't answer any questions by email. But let me know if you have any questions that need answering. Have a wonderful evening, and I will see you tomorrow.